Let's continue with a symbolic solution. This is something that some people have to get used to a little bit, and we start this by clearing our memory, our workspace, and by clearing what is written in the control window. Have it a little bit nicer. If I start a new script, how do we get about in getting symbolic solutions to differential equations, and specifically sets of differential equations, namely more than one differential equations? So what we have to do when we work symbolically, we have to define the symbols that we are interested in. So in order not to confuse them with the previous ones, I give them slightly different names, and the variables that we are interested in are x1 and x2. And to leave it simple, this will be all that we are going to consider. So what do we have to do? Now we want to have our symbolic functions, and we know we have two symbolic functions, f1 and f2. So we can start by writing this. What do they look like? Ideally, I would have written it here. So my first function, I can just copy it over. We have, in this case, written our expression for the differential equations with the numerical values of the parameters directly fit into the function. So rather than saying a here, which I could do, I could of course use a here, but I would have to define a symbolic variable called a. If we don't do this, then we can fit in the numerical value, which is 1, and all the parameters as given, and you can see them in the slides. Then this would complete my definition of the first symbolic equation according to our model. Now the second equation is pretty straightforward to write in. It's just x1 minus x2, and I suppress output by stopping the command with a semicolon. So this is our function definition. How do we get solutions from symbolic manipulations? What we're going to use a function which is called solve. Solve is the way of symbolically solving differential equations, means we can give some condition for which we want to have an explicit expression of x1 and x2 of our two variables, or if you think experimentally, of our two measurables. So we need to solve. Well, it's easy. Similarly to before, now we define what functions do we solve over. Well, we have two, so we put them in an array. One is called f1, the other is called f2. If we put them as an array, solve will understand that we want to have them solved simultaneously. Right, now the condition, unlike fsolve, which the symbolic solve doesn't know, we must tell what we want to have this equation, and our steady state conditions is no change of both of these equations. So both equations set equal to 0, which we have expressed. And note that rather than saying just simply equal, we have to use equal, which is the symbolic way of saying something is equal to something. So we are using here a Boolean expression of equating things symbolically. And we are finished with this in principle, except that we need to store our output somewhere, because solve will give us a solution both in x1 and in x2. We expect two outputs. So to get multiple output, we have to assign them to an array, and this array is now defined by our two variables. What are our two variables? Let's call them x1 is s, saying this the steady state of x1, and our second will be the steady state of x2. So now we say, give me two output arrays, one called x1 steady state and the other x2 steady state, and from there I can take them for further manipulation, for example, for inspection. If we terminate this again with a semicolon to suppress output, we can execute this little piece of code and see what we get from it. Well, actually nothing is visible now, because I have suppressed output. However, if you look into your working memory, you can see that these values of x1 ss and x2 ss are already there. Yes, I can find them. And surprisingly, if I look at them, what they look like, you can see that they don't give numerical values, but they are actually given as expressions. And this is typical output from the symbolic dynamic, from the symbolic manipulation. You get an expression as an output. So of course we'll say that's very wonderful, but it looks extremely complicated. It involves taking a square root, and you have to divide something by 20 and so on. So actually we don't really want to see these expressions, but we want to have the numerical value. We want to see what is the numerical value of x1 and x2. In order to get this from an expression, we use function eval. That's short for evaluate. Evaluate some expression, and we can just put in what we have. So we have x1 steady state, and we have eval x2 steady state. So if we look at what this gives us now, we get two answers. The first is the answer for x1, and the second is the answer for x2. Now there's something that should surprise you. Namely, we get two outputs. We don't get one number, but for each variable, for x1, we get two values, and for x2, we get two values. Why is that? Well, we can just ask, what is the equation, what is the function supposed to give us? Solve is going to give us all situations under which this set of differential equations becomes equal to 0. Right? So what we have is there are actually two situations under which this differential equation can become 0, namely one where we have the first value for x1 and the first value for x2, and one where we have the second value for x1 and x2. How do we determine what to look at? Well, it's fairly easy in this case. As you can see, one of the values is 3.1127, which is some value, but the other value is negative. And negative concentrations don't make a lot of sense. So rather than looking at the second concentration at all, which is not a realistic solution of what we want to have, namely a positive concentration value, we only look at the first value of each steady state. So while we have found that there are two principal theoretical steady states, only one is experimentally realistic, namely the first one, positive values. And if we now, let me clear this window again, make it easy, and then redo our code. And this little bit of code now tells you that our first value is equal to 3.1127, which is same as we had algebraically, of course, and the second value is equal to that one because we know both must be equal. So you can see how, in a very straightforward way, by symbol manipulation, you can also get the numerical values of the steady states using solve function as suggested here. Right? So we have done these three exercises that have helped us to find steady state solutions. However, we know from looking at our EPO model, which was introduced in the materials for this session, and as you can also see from the data and from the simulations that have to do with the physiological model of the assignment, steady state is not the only thing that we are interested in. So in order to get a look at what other things we can expect from this model, I close down this script that we have written here. You can also have it in the download materials. And now hand over to Rob for a quick look into how we can simulate this model that we have here. And Rob, please.